Right, first slide. So who's heard of Moxons? Quite a lot of you. Did you know that was, yeah, okay, next slide. Oh, I can go back to the first one.
Yeah.
Go back to the first one.
Oh.
I just want to say, because you guys have seen a lot of VHF, UHF antennas. You haven't seen the whole gamut. But I'd like to talk about a couple of other ones that you may not have heard of, although most of you probably have, but some people watching may not. So I'm not going to do corner reflectors, zigzags, microfield, cones, sphericals today, but maybe next time. Okay, next slide. So let's start with Mr. Moxon. He basically got his idea from Fred Caton, VK2NO. Has anybody heard of Fred Caton? So back in 1973, Fred Caton got a Yagi Udason antenna, and he wanted to make a square one because he had space issues. So he folded all the sides in to make a square, and then he separated it with buttons, big coat buttons. And so it didn't work out quite well, didn't have enough gain or anything like that. So Les Moxon picked up on that. Like Fred Caton did this in like 1973. Les Moxon picked up on it around the early 90s, 91, 92. And he thought, well, I'm going to get a Yagi and turn it into a rectangle because it's not going to have that much loss actually. And you can see from here that it's quite a simple antenna. So if I draw one here, that makes too big here. Yeah, it's has a parasitic reflector, like a Yagi antenna, and it's a very simple thing. Some people do extra things. Some people make a 3-element Moxon. Anyone heard of a 3-element Moxon? Yeah. They actually put another element down here. Sorry, that's all very straight. They do something like that, which is interesting, and some people like to put more on there to get a bit more direction, because you've got the where you feed it in here, and the direction is here. The reflector points it this way. And the reflector's slightly longer just so they can handle the phase differences. That's how they usually work on those things. So this one picks up all the transmission, points it that way. Now other people have done different things with Moxons. It's magnetic, that's pretty good. Some people do multi-band Moxons. So they would have so you need a brace, and then they start to add bands like that. So you could, for example, have a 10, 6 and 3 metre Moxon all on the one pole.
Separate feed?
You can do separate feed if you want, but I've heard that you can use a straight feed. You don't need traps or anything, it just finds a frequency you want. So that one goes down there. You know, it's a bit rough, but you get the idea anyway. And the other thing that some people do, a lot of rubbing out. Some people stack them, so they may have then another one underneath. Okay. And they can have another one under there like that, just to give you more gain, they say. So your pole, you have a support pole there for feed.
Or you can have different band Moxons.
Yeah, you can have different band Moxons. So you can have a 10-6-2, you can have a 6-2-70, something like that. And they work quite well. So I'll go back to just the standard Moxon, because today I'm going to show you how to make a pretty standard looking Moxon. Just draw that a little bit better. So you have a separation in there, and I'll tell you about that shortly. So I'll go to the next slide. So I started modelling one up in neck. It's pretty straightforward, easy thing to do for these. You can get a whole library of these here online, download one to find them. But then I had to modify it for the size that I wanted. And I wanted to test whether the size would work or not. So I go on that slide. That size that I came up with, because I wanted a portable one, gave me that kind of, see the beam with it, it's very generous beam width. I think they're actually better, that's better than the argument, because it's more broader and it's not critical where you're going to aim your antenna. And you can see the reflection line there, it's straight enough to write a linear equation for that, it's so straight. So I thought, is that really going to work? So I thought I'd make one.
So that's in the same plane.
That's in the same plane. So this is very portable, Moxon, very easy to make. I use some junk there from Johnson Street. I might get my radio out of my bag.
What's in the middle of the top?
This is too short,
Oh, I
so I need a bigger piece
Right, okay.
just to hold it together. Sometimes you can't
Well, it
get
was
it
a
right.
resistor or something another way.
Zero.
I couldn't resist putting it.
A zero.
That way. Just bring my bag up. I'll just put the radio. Bring my radio up. So I wanted something so lightweight and portable. Cousin comes to the rescue because I forget things all the time. Like this is my car, and it just sits on top like that. Now, because of driven element and the reflectors like that, it's going to go that way. You could have it that way if you want. In fact, the ones if you want to do 3, 10, 10 and 6 and 2, if you want to build those, you can have them vertically or you can have them horizontally.
But that's just bits of dowel, isn't it?
That's just bits of down.
Yeah.
So I'm thinking the estimates in the middle. I'm probably not going to ping anything in here because it's a Faraday cage, isn't it?
You'd be surprised.
Three poles.
Try the local one.
What's a typical game?
About 16 there.
That's pretty good.
Getting something. That's good.
That's the idea of the small scale.
Yes. Pretty much what it was. I'll just stick it out there, I'm sure I'll get it. I won't do that. So this is a very easy thing to make. You might want to use thicker metal so you don't need a dowel there. I originally had a chopstick on there. You want to go to the next slide. You could also do a 3D mount, 3D printing one. Oh, and you'd probably do a nice little triangle up there, which would work over this and keep it more stable. So next slide. Oh wait, I'll look at the next one. This in case anybody wants to know. So it's 74 centimeters, 15, 10, 10. So if anyone wants to make this sort, I had this sitting on my table, I hadn't even finished it, I'm pinged into the Somersby, and I'm at water, and I rarely get into Somersby as it is. So, and also with this, okay, you need a dowel, right? You need a dowel to separate the parasitic from the driven element. Now the dowel itself, it's got a bigger version of it here. You want to go in 1 centimetre that way, 1 centimetre that way, you leave 4 centimetres this way.
Critical? Or you just need an air gap?
You need an air gap, and it's somewhat critical. I tried in neck to have it more separated, and I've got different plot readings, of course. I'll have the SWI going a little bit. So I found this was the ideal sweet spot. So all I did was I got the dowel, put the drill in, and then you had it in 10 mil sticking out, so drill it in. And you have how I was going, just glued it in. So that's
So the non-driven element is the reflector.
it's a reflector. Yes, parasitic reflector, just like an artist.
He said, so it'd be better if, rather than just put it on your radio, because you're holding the radio.
I've had this sitting on a tripod.
Yeah,
I've got an stomach screen on this outside,
Yeah.
sticking up out of the radio.
Yeah.
And I thought that was a real ripper.
Yeah.
I thought it was really good. But, what can I say? Yeah, that's when I first made it. She put a chopstick in there. I don't know what chopstick is now. Just to keep it sort of in shape. You don't have to cut off the connector up there and get all plastic. But you can see the reflection curve on there, on the reading.
Yeah.
And that's pretty good on the VNA. I'm quite happy with it. I forgot to put the Smith in there, but the Smith sits pretty well with the small semi-circle in the middle. So the middle is the area that we want it, so I was really happy with that. That worked really well. But yes, you can put that on a tripod. I've had it on a little tripod on my desk, so the cable coming up to the radio. It works well, you just rotate it or whatever. That's how it works. I'm very happy
So
with
it's
it.
actually it's actually firing towards the connector.
Yes, it is.
Yeah. So you probably don't want it when you're
That's what I was thinking.
Yeah.
Well, I'm only using 5 watts on this.
Yeah, I know.
I was thinking in the radio.
This hand's
No,
only
don't worry about that. I'm just thinking that, if you have it like this, like this, it's a kind of waste because it's
Yeah.
going
Oh, I know. That's why I have it on something else.
Yeah.
Like a tripod or something like that. But if you want to go portable, it still works very well because the bandwidth is really, really generous. So, yeah, you want to pan it around if you like.
Really,
We don't want
Pass it on.
yeah.
So you can use cheap dowel, you can use thicker metal, whatever you like.
Never mind. What I'm thinking, because you're holding this, it's basically going into the radio, direct swinging into the radio. If you reversed it and used the outer length as director,
Yeah, you can do that.
in that way you're not going to be,
Yeah, I thought about making a rig for that sort of thing.
instead of a driven element reflector, driven element director.
That's right. That's right.
And if you have a hold the right position for you, you are a reflector.
I know, I'm a pretty good reflector, aren't I? Not saying it, but. All right, any more questions on boxes?
Sorry, what was that little central piece there on
That's just a
joiner?
It's just a joiner, so,
Zero resistance.
yeah, I just cut the plastic off, I don't grow with it. It's thinking, oh god, this is too short, this piece of metal I got from that. So this whole thing cost me $8. $8 for the metal, cost for the dowel. The most expensive thing was the BNC connector, which I got here, I think it was $10 for it. So I got it down to 5.
Yeah, sorry, what was it for, that little connector in the middle of the back?
That's just a joiner.
It's just a BNC.
No, that's not. Oh,
Oh, at the top, that's only because I got a short wire. All I had was a short wire, I didn't have anything long enough that I could bend around.
Oh,
So I had to join it somewhere, I thought I'd join it in the middle instead of on the side or something like that.
That's fine. You think it's an active part of some sort.
Well, I have to say the antenna was really, really low. So I've pinged most of the repeaters around New South Wales, well, Sydney anyway. So Wollongong, I've got Wollongong, I've got Somerset, got Hornsby, which doesn't always work very well. So there you are. Other antennas. Who's heard of halos?
Yes.
Yes.
Oh, yeah. Aren't they fun?
Didn't work.
Some of the older ones, these came out around the late 40s. Some of the older ones, they're stacking it like I showed you on the box, and that's to get you the broader bandwidth on them. But the later ones, they use the gamma match on them. Like you see, you've been making them for handhelds. And I saw a handheld one of the last Trash and Treasure, I think about that big, I thought, this is really neat. Maybe we can track down that guy on 2 meters.
So the benefit is direction one.
No, they actually have a normal mode radiation.
So what's the benefit?
Changes.
Makes your car look better.
Yeah, makes it fun, better. But you can't change that to a loop if you wanted to. That's got a shorting bar on it.
Right.
The thing is that you can use the halo as a
the horizontal antenna on bed.
Right.
Yeah, which is what they always used to use it for.
Yes.
Even,
That's why.
I think some of the authorities have to make them look more official or something. Next one. So here's a diagram. Here's another one you can make. That's a very straightforward one for 2 metres. It's got the boarding bar there, which they call the gamma match. You can put a capacitor, put a trimmer cap in to start with, if you're not quite sure on the VSWR, and then you can take it out when you get it right. But the shorting bar itself, that can move, so that's like a clamp. So that's oops. So you've all seen the box and you don't want to see that again. So clamp.
Much better. Yeah, mini is not. I didn't wouldn't string.
So that's all it is. But the shorting bar has like 2 clamps. And it just moves that way or that way to visual VSWR. And they do quite a good antenna. I've heard they're about 60 there. Don't know how, so I haven't looked at my antenna. Because I want to move on with the other antennas. I just want to show you all kinds of different antennas. Okay. Any questions on halos?
Variation of that as well.
Yeah, that's true.
Have you modelled that design?
I haven't modelled that in there. There's something else coming up that I've modelled. And I modelled that in that lab, not getting to that.
Thank you.
So next slide.
So is that the same as like a loop bearing, like what's known as a loop bearing? It's working on a different principle.
It's not directional.
It's not
so
magnetic,
it's horizontal. If you had it vertical, you might be able to modify the shorting bar, make it a rotate it. I don't know. Colin's the expert on it. Actually, come on a minute.
But like what I'm doing is, how is that like physically different from a loop bearing?
Well, it's not physically.
I think it's more the size.
And what
It's
what
not
is
a
the
antenna.
you're driving it with?
2 metres.
No, but if you were driving it with HF,
Oh,
then it'd be less than 1/8 of a.
yeah, you'd have to make it much
And
bigger.
then it would be then it would be a magnetic loop.
That's right.
But if you're driving at 2 metres, then it's just a normal.
It's a normal mode. It's not omnidirectional. And here's another one that you can look up online. These are fun. These helicals are fun. They're easy to make. You can see in the diagram they've got shorting straps in there. Little bucket spots to
Yep.
make it match. And these are also normal mode.
What are you driving? Are you driving the little loop or the big loop?
The little loop.
The little loop. Yeah.
And so those sort of things. That's normal mode.
Is that radiation pattern good for satellite work?
Not necessarily.
Well, where's?
I'll tell you in a minute what is.
Right.
Careful,
That's normal mode. Omnidirectional. The other way of doing the helical is axial mode. Goes this way, runs along. For that. Which is what my next slide is. So helix antennas, I really love these. They're kind of crazy things, aren't they? They're mostly made for comsats, high frequencies. A lot of interesting things about them. But firstly, I'll this out again.
Oh, we have a sample coming out.
Exterminate.
Not yet. Not yet. Not yet. Leave it there. Leave it there.
Distracting everyone. That's his job. What to distract?
Oh dear. Just can't.
Can't get good,
It's like
man.
trying to run a show, you know, and something gets out of sync.
Hard to find good help.
Okay, I was going to talk to you about circular polarisation, because that's what these things are. They're travelling wave antennas.
This is for satellites.
Mostly for satellites, but when John Krause invented it, there were no satellites. It was like 1946. He made a seminal book called Antennas, which is all about these things.
Catch a title.
Just talk about the polarisation. So
Expensive.
going from the right-hand polarisation. Circular polarisation. You could do left-hand circular polarisation, but most of them are on the right side because most receiving antennas, vertical or horizontal, actually receive those transmissions quite well. But if you have a left-hand horizontal polarised, not so well, especially if you're using a right-hand transmitting to a left-hand circularly wound antenna. It's interesting, isn't it? It just won't accept it. Some government organisations use left-hand polarisation because of security or what have you, and they don't want any interference from other antennas. That's why they go left hand. Most of them are right hand.
But if you bounce off a wall, it's going to swap the polarisation.
Well, I'm not bouncing it off the wall. I'm only using a reflector.
Space, right?
I wouldn't want to use it in here.
No, the moon, yes, of course.
But anyway, okay, can anybody guess?
It means, I'd say 23 centimetres. Where we are in the world, you always transmit up right hand and come back down left hand. You don't have to worry about your antenna orientation.
Can anybody guess how Krause came up with the idea?
Yeah, the nightmare.
Somebody wound him up?
Yes, the slinky.
Yeah, slinky antennas, aren't they fun?
Yes.
But they're normal mode antennas.
Down like plastic.
I'll give you a clue. I don't know if I can draw this, but I'll try. So, oops, like that. Talk amongst yourselves and like this.
Believe in low SWR.
That's right. No, it's not that I don't believe in it, particularly these frequencies, but it's not a feature of an antenna. Anything can be next to anything else.
So, this is really interesting.
My radio don't like it. Unless you've got a valve.
So, anybody know what that is? Anybody heard of a klystron?
Oh, yeah.
Klystron? So, Krause had a friend, Dr. Raines. He went to a symposium on microwave transmitters. And they were usually working with klystrons, which have cavities. And then he came up with this, Dr. Raines came up with this, which is a travelling wave electron beam gun. So you've got your gun here, your anode and cathode. You've got your collector here. And the RF goes in, goes out, and acts as a kind of an active. And that's where he got his idea from. And he said to Krause said to Raines, I think it's a great idea for a travelling wave antenna because it's moving from left to right. And Dr. Raines says, well, it hasn't really worked. Give it a go. And this was in the microwave area. So that's where he got his idea from.
How long ago? How long ago?
1947. Before you go back a bit, there's another funny story. My father was in the Air Force, and he had another friend who was in the American Air Force who had some connection with Area 51. Because there were no satellites, Krause's antennas were used in a place called Jackass Flats down in Area 51 in the Flat Desert. There's a little side of a hill where they built storage room where they put vertical takeoff jets and they put circular polarised antennas as well. And they used these antennas in the early 60s to talk to high altitude spy pilots and spy aircraft on the Lockheed A-12 they call the Oxcar. And that's what they used. And they had like 30 elements in there, 30 segments. So a very high gain. A typical gain on these things would be 15.
Wow, that's right.
But you lose the advantage. You get about the 3D with it, 3D
Yeah, yeah,
on
yeah.
a turn.
Start
Get to the
losing.
10th one, the grades goes down to 2.5 and goes to 2. But some people still use 30, and back in those days, they had like these things stacked with 30 tons. It's pretty amazing. Okay, so,
Are they very directional? I mean,
yeah, that's what they're for. They're
what sort of beam width do you think?
Oh,
Well, it's not
right.
beam width.
It's very narrow. It's a very narrow beam. So it'll be something like, and I'll do 2 of these just to show a different example. So I'll just do the half. So if you've got a straight reflector, like a circular reflector, standard isotropic thing, it'll be a couple of back lobes. I won't wipe that out because it's confusing at the moment. A couple of back lobes, a couple of little front lobes, and it'll be something like that. It looks a bit rude, but there you go. But if you use a conical reflector, this is a whole other area here. We used to do these on real estate. Oh no, I didn't hear that. So you use a conical reflector, say, like the one I found in the junk pile. You eliminate most of your back lobes, and the thing would be more like this. It would be a lot fatter.
Oh.
I think that guy needs to see a doctor.
With the same gain?
More gain.
More
You get
gain.
more gain.
So
I found a conical one in the Horse Scrap. Cost me $5. It wasn't a satellite dish or anything like that. It was actually a downlight from the foyer of the hotel. Oh. Being demolished. So I thought there were 2 of them.
What a happy.
So I thought, this looks really good. I can use this as a reflector. It sort of curves out a little bit. It's not being slightly. But anyway, here are the ways to calculate the size of the antenna. Obviously, Krauss, he focused on high frequency. And you need one circumference or one wavelength. Like for microwave, that's fine, not very big. If you want to go down the band a bit, you have to get a lot bigger. So turn spacing of 2 a wavelength, reflect the diameter. You could go half a wavelength. Krauss has said that in his book. But see, he doesn't say very often. Wavelength is the diameter, not the circumference. So if you want to make something for the lower band, you want to oh look, that's too rude. So say you want to be really silly idiot and do a 2 meter helix. That's a huge. You're going to have a huge. It's going to be bigger than this. I'll to show you because I made one. That's not even 64. So how do you do it? So circumference divided by pi equals diameter. Very simple. So 2 meters divided by 3.14159, etc. If you wanted to, gives you roughly 64 centimeter diameter. This is about 55, so it's not even that. I actually need an oil drum, which is about 64 wide, so I can make it this performant. But you can see how big it is. Let's go to the next.
Choose the appropriate size diameter tire.
Tire.
Tire. You've got the right size.
I need a truck tire, right?
Scooter tire.
Yes. That'd be good, wouldn't it? I'll just go back a bit. So you can see here, diameter is 0.94 away from the same there. Calculators to say 1 wavelength. But we've got to consider pitch. So away. You've got to consider so many things to make this bloody antenna successful. So say this is just a cross section, turn spacing,
You haven't even mentioned velocity factor.
No, I haven't. It's light. It's travelling.
Yeah, all right, okay.
Also pitch. So the pitch, you drop it down. Lower angle pitch. Krauss says about 10 to 24 degree pitch. It's ideal. Okay, so I used Krauss formula to make mine, but I had a look at some of these others. They're not a good calculator. There's also ARNSW, which is a really good one. But I use MATLAB here. And MATLAB, you can overlay your helical input suggested beam cut. And you can add enough an elevation in that. So that's really good. A lot of the other ones don't tell you that. It's just a model. I didn't want to go full MATLAB. You can see here I circled some of the calculations. For a 2 metre antenna, you've got to have spacing between times 410 millimetres. How ridiculous is that? That's huge, right? So I found that some of these calculators are just not accurate enough for the lower bands. And Krauss hadn't really considered lower bounds when we did this. So I did make one this size, 5 turns, and it worked. It was just too big, it can't fit it on the car. So one of the things that Krauss did not consider so much was half-wave. Of course you need full wave for microwave. What if you try half-wave for 2 metres, for example? I thought, I might try this. I looked around everywhere, I couldn't find anyone else who's done this before. So it may be a first. So let's go on to the next. So I did my concept. Once I went to Awesome Scrap and got my cone, I did the concept for this. Now, Brad, we can bring it out.
Drum roll.
No, I'll get it too. Don't carry the whole thing. Stand by.
Well, this is certainly a design. Every home should have one.
If I put that in my backyard, the neighbours would freak.
And that's just to get television. A little bit. Oh my God.
I know it's a crazy antenna, but it actually works.
That is unbelievable.
I was going to say that I can pass it around.
Who are we going to irradiate today?
Carry on. All right.
Oh my God. Oh, this.
All right. It's because they have a project.
What's that?
Oh,
So, what's the mechanical issues? The formulas are easy compared to this.
What frequency is
This is 2 metres. This is what I call,
so this is a halfway.
this is a halfway that's never been done before.
Oh.
This has not been, proper
It's
halfway.
halfway in the diameter for each
Well, it's
helix.
Yeah,
yeah.
yeah,
And there's a couple of them.
yes, yes. So,
Is there another frequency that it hits?
this actually works on 70 centimetres.
Yeah,
Not
I'm
so
just
great, not so great. So,
No.
mechanical issues. Now, I wanted to do a couple of things. I wanted to try doing a movable one so I could just get different assessments in MATLAB by changing the turn space and all that. So I was thinking of doing another round on here, and then making loose on top, and go forward or back, and then getting another length of this. So it just makes it unwieldy. But this is possibly the world's only 2 metre.
Or not?
Yeah, it's a 8. It starts at 1, there, 2, so it's an 8 turn.
So we're a part of history. We're a part of history.
Which are part of history. So this is possibly the only halfway 2
You
metre
apply for a patent?
portable.
Apply for a patent yet?
Another one. But this does assemble. This does disassemble. I actually fit in my car, and I haven't got a very big car.
How long does it take to reassemble?
Not that long. About 5 minutes.
What's a 10, isn't it?
Hmm?
What's a 10, isn't it?
Yeah.
It's a degree.
So some people use metal central support. I didn't want to. Why? Some people, if you see in the documentation, I've read a lot of documentation on these antennas. Some have used central metal supports. I just wanted the dielectric constant was even all the way along. So
That's wood, yes?
yeah, so that's wood.
To me, that makes sense.
These are PVC standoffs, which I had to go on eBay because I couldn't find them anywhere else. They're industrial strength, they said. That's what they said. I could drill a hole through it easily. If I was using little valves like that, say on the Moxon antenna, they'd split. They'd do all kinds of things. So I thought I'd use this. What else? And so the gain, I've got to use a whiteboard to show you the gain, but this is in the way. It's not looking but there are other things to consider. One of the fundamental ones, centre of gravity. If I don't have these legs out, it's going to tip over. It's going to go like that.
Yeah.
So I thought, why don't I make up a radio cradle? Now, this is junk. This is paper towel holder from the restroom. I thought about it getting screwed on. I sort of think of what I want and figure what exists. So it's just a 2-metre radio in there.
Yes.
So that just sits on.
Oh, and that gives it sort of balance.
That gives you a counterbalance.
It's a counterweight.
Wow.
What is that?
Is that got batteries in it?
There's got a battery in there.
Yep.
Not in the radio, I've got a lithium hanging off the
What
side.
frequency are you on? But what, yeah.
I can't get anything in here. I'm setting this first, don't I?
So does the shape of the reflector have any effect, or is that good enough?
I think the shape is acceptable. Ideally, I like it wider. You can make it out of any material. Like I thought about getting a big metal aluminum frame and then using metal fly screen, and that would work equally well as long as it was slight conical. That would work quite well. So that's halfway. The crowd book said the halfway length isotropic reflector is okay.
How did you get on feeding that?
Matching section.
How did I get on feeding?
How do you feed it? How do you know where to feed it?
Is there a feeding matching section somewhere?
Yes, so okay, let's go to the next slide. So that's the raw result. I haven't done any impedance matching. You can use a stub or a variable impedance transformer. So once I put the transformer in and put a stub in, so this basically a stub is like a quarter wavelength. And you can loop it, you can keep it open, or you can short it. It just depends what frequency you're on. If we go to the next slide, after matching, 2-metre one is beautiful. You can see it on the left there. You can see it's quite a low VSWR. And the 70 centimetres, not so great. When I put a choke on, it's a little bit better. But that worked quite well. I'm quite happy with that thing. Smith is right in the middle, which is just slightly on the capacitance side. But that's okay. I'm very happy with it. I got good results too. I got into Queensland on this. On, what was it, 144, 100. Got into Tasmania. And I think most of the repeaters.
Sorry, FM?
FM on the repeaters, sideband.
Oh,
Yes, sideband. 144, 100. The only annoying thing about 2 metres is there's not many people on it. It's frustration. So maybe I can look for a CubeSat or something like that instead. But ideally, I would, if I had the money, I would have this as a satellite tracking on a gimbal that goes up and down like that and rotates and does it automatically with the frequencies either side, so you can counter the Doppler effect, all that sort of stuff. But at the moment, just having fun on VHF, UHF field days with this thing.
well, it certainly stands out.
Yeah,
Carmel, may I take a photograph of you with that area?
sure.
you said you got into Queensland and Tasmania with it. Was that by direct?
That was direct. I might have been lucky, it might have been ducting.
What was the distance?
Yeah, I'd say it was ducting. It was quite hot days when I was doing it.
What was the distance and what was the power?
Power on the FT230 is 3 watts.
That's brilliant.
So
And distance?
Queensland, how far is, well, he was just on the other, he said he just got back from Mount Warning, so he's on the other side of Twin Towns. So it's just on the other side of the border.
I think you would have calculated this.
No, I don't remember.
From paper design to fabrication, what sort of time are
But
we
to build this,
well, from designing it right through to fabricating what you have?
Well, research first.
oh, lots of research first.
Yeah,
It took me
absolutely.
a while. And then just trying to find a material that would work. I mean, the calculations vary too, depending on the thickness of copper, this is like something, right? And it also affects your gain as well. I'm going to show you.
And there's downtime during the project.
How do you like getting sick? Yeah, getting sick.
And does the thickness of the radiator, you know, basically, the wire, does that also affect the bandwidth? Lower
No,
to the other?
not necessarily.
Really?
No.
Okay.
But it can affect your gain for some reason, I don't know why. More research I need to do for that. But as it is, a halfway 2 metre antenna that works, it gives me, try to trip over my, gives me roughly
3 watts.
1.5 to 1 on the Hornsby repeater, so that's not bad. Too much of the Faraday cage in here. Okay, what else is I going to do?
Oh, that's interesting.
I just need to move.
Oh, exactly.
Trust me, I can't pick up anything to make it. I just want to know if I can do it, that's all. Because you see all the other attendants think, oh yeah, that's interesting, that's interesting. But the fact that the thing works, I'm really happy with kind of jumping up to joy that it's actually working. I just quickly, Kraus did one study. Somebody help me move this. Out of the way a little bit, so you can see the board.
Take the chair away.
It's just that way.
Without getting the TV.
Tap in. Paper.
Yep.
Yep.
Might work better though.
Oh, that'd be great, wouldn't it? Are you? Oh, I'll bring it up to your place. We could try it on Henry's place as well. Oh, yeah, Kraus did on a, I remember the diagram, I just can't remember how much detail, it was something like this. So I'll start at 4. That will be. So that'll be the peak dBi. Now you've got the one wavelength. So, circumference. So that'll be one wavelength. This will be 1.25. There are a couple of curves that he was trying at different frequencies. So, different turns, now you got 8 turns. It kind of came out like this. So 8 turns, 1 wavelength, would get you about 8 dB.
Sorry, what was the last comment? Would get you what?
8 dB.
8 dB, right, sorry,
or something like
in
that,
here.
with 8 turns. So, no, sorry, that was 5 turns, that's right, so that's 5. Then, turns would increase as you increase. So the gain would increase as you increase turns. So that would be 10 turns. And the last one that he did, something like 15. So between here and half a wavelength, there's not a lot of difference in it, in the amount of gain you get, even though the circumference is smaller. So I thought, okay, I'm going to do it.
Of course,
I know, no.
the more turns, the bigger the thing, more mechanical.
Yeah, I don't want to do that. I don't want to do that. Next slide.
Oh, here it is.
Oh, you guys must be getting hungry.
You want to get food or you can have the slides? Which one?
No, this is really interesting. Keep going.
So, halfway circumference stimulation, halfway reflected diameter, very expensive experiment, not done before, and not as far as I know, considered by crowds for the little hands. So, originally, it was about, before I matched it, about 140 ohm or so, so use a stub or a frequency transformer. You can use some of the high frequency ones and use little matching strips up the bottom of the reflector. So return loss very good. 70 centimetres not so good, something like 7 dB. But on 2 metres is anywhere from 16 dB to 19 dB, which means that it's about 95% efficient, which is really good. You know all about how return loss works. So 75 millivolts. So you can adjust the turn spacing, get more directivity. That'll flatten out your beamwidth, and you get more gain as well. So inside my house, I can get into Somersby. I can rotate it so there's no signal. I've got a wave meter in my bag. I can show it later if you like. Our standard design, okay. So the design's been around since the 40s. You think, well, the helical is a helical is a helical, but it's not always a helical. Who's heard of the stub helical? That's a USPTO pattern. So say you've got the circumference this big, and you want something smaller than that. You want to get away with it. What do? You introduce stubs.
Oh.
Yes. So what's that?
It's a virtual increase in
So virtually the same performance.
same circumference.
Same performance.
Just different.
Yeah, just different.
Yeah,
Yeah.
different. How do you say it? Design, I guess.
A different design.
Yeah.
What
It's
about
small.
helical within
It's
the
a,
helical?
what?
Helical within the helical?
No, that's
No, it's
this replaces that
compressed.
size. So it makes it smaller, more compact, more usable.
Yeah, okay.
It's pretty neat.
And
You're
is
right.
sorry, it's a problem.
You make the
You still have the winding,
helical
so it's
to
still
make it longer, but smaller diameter.
smaller diameter. So you can get more turn spacing, you get more.
Yeah, like a spiral with the spiral.
It'll still be a spiral, so with the I need some time off. So your normal one comes, I'll get rid of him. So have I been speaking too long? Sorry about that. So that's your normal one. That's how you measure your circumference, where it meets. Up there. So in the stub, it's going to continue on. It'll have.
Is the regularity of those stubs critical?
It can be.
Yeah.
I don't know enough about it. I've got to read through the patent.
Right.
The patent's been around for about 20 years.
There could be another thought. What about surrounding the wire in the helical with, say, a dielectric material to reduce the velocity? Say you use, say, inch diameter Teflon around your 1/8 inch diameter wire.
Yeah, might work.
You should try it.
Okay.
You can do that
Oh,
with
yes.
sage.
That would be very similar.
You want
On that main.
It's like fractal antenna.
a what?
Oh, yeah. Yeah. See.
For fractal.
I could slide it in.
Looks like.
So down the bottom, I was in the park testing this,
Oh, yes.
and I heard a
What
signal.
are you doing, madam?
There was a park ranger there. A signal was over there. Park ranger happened to be there just as I said. He said, "Oh, what are you doing?" I did that.
Get out of my way, I'll vaporise you.
Well, I looked past the reflector. He was gone.
Oh, yeah?
Where the hell did he go? Did he run off or something?
Ah, that's a benefit.
So that's a good thing for a park
He
ranger.
would be in the line of the disruptor ray.
Does it work on parking cops too?
What?
Does it work on parking police?
Oh, wish.
It could be a car.
Put this on top of the car.
You know there's a big market for this in the movie industry.
Yeah, there's a
All
thought.
black market.
Next slide.
So it's a different.
Yeah, that's right.
Okay, that's it. They're not really new because it's just out of the Mooney Hall versus the flying saucers from 1950. Just for fun. So there you are. Any other questions?
Oh,
Who's missing the big industrial landscape?
Oh, they came out of the demolished hotel.
ah,
Okay, the question, you were talking about a right-handed polarised helical to a right-handed polarised helical
Yeah.
at each end.
Yeah.
How does it work if the other end's got just a linear antenna, either horizontal or
It'll
vertical?
receive it okay. It's when you have a left hand polarised, it doesn't receive it. The left hand doesn't receive it as well as a regular antenna. It wouldn't receive the right hand polarisation
Now, why are they used for satellites?
because they're very direct.
Huh?
You can get a very narrow beam, so they're very direct. You can pinpoint satellite and you can track it.
Satellites also tumble, like with our amateur satellites. So obviously you don't have to bother with rotating your aerial if you've got a circular pole.
True.
Let's hope it's something in the right direction.
Yes, travelling in the right direction. And I've got to say one other thing, I don't think I've said this. These are not resonant antennas. There's a bit of hoo-ha about resonant antennas because you only get a resonant antenna on one frequency. Sure, you can get the other one. This will never be quite a resonant, but you'll get pretty broadband flat VSWR on it anyway. So there you are.
Could you use tubes without losing
Can. Yeah. Yeah. I've seen people get thick pipes, thick PVC pipes, and just wrap it around the pipe.
Yeah, 110 mil height is very good, 23 centimetres.
Yeah, exactly. So for 2 metres, it's a bit ridiculous. So there you are.
So you've just used straight copper tube, Teflon line, coax.
Yeah, you can do that. Yeah, it's a sort of there for them.
I think it's
This piece on the bench,
Oh, that? Oh, that's got a joiner in there. So it's going one of the rods, expand it.
oh, I see.
That's all it is. And a solid, yeah. I need a super hot solid station on
wow.
that. There you are.
Thank you very much.
Fun, huh?
Brilliant. Brilliant.
Stay there, please, Carmel. Rafi and Colin up on stage, please.
That'll be this.
Nowhere near as exciting as that one.
Not behind me, not behind me. Members, these presenters have given up their time to come in here to enlighten us, which I think is an excellent effort. So give them a round of applause. Also, before we break for lunch, if you can take the chairs and put them at the tables, with a single table, probably about 6, 7, maybe 8 chairs to a table. that'd be great. And at the very end, after lunch, put the tables and chairs away. We put the AR New South Wales and the board puts these on for the benefit of members. And if there are future topics that you people would like to hear, provided we have someone who can speak to it, and I get the information, the contact numbers, we're happy to do it. If it's a topic that sort of no one really is interested in, we won't put it on. So if you think of something, come and see me, okay?